I need to once more just talk about sponsorship and recognize our lead sponsors. Again, a large grant from Dr. Mary Morgan Finnegan, Dartmouth class of 1986, really kicked this whole thing off and got Kathy Lambert and myself working on this over a year ago. And the George Link Environmental Awareness Lecture, David Orr's keynote this evening, is sponsored by the Dartmouth Environmental Studies Program. Andy Friedland is the chair of that. The Newcomb Institute for Computational Science at Dartmouth, Dr. Hani Farid, the director, is a platinum sponsor. Public Service of New Hampshire, Randy Dixon, platinum sponsor as well. Low and Window Center of Vermont, New Hampshire, gold sponsor, and our silver sponsors, Bond, Second Wind Water Systems, and Wright Ryan Construction Incorporated. So, this session, we wanted to bring some practicing architects and landscape architects here to talk about where they see their work headed, having become very familiar with the LEED process and moving beyond LEED towards regenerative architecture and living buildings. So we're really pleased to have these three folks here today. Jose Alminana is a landscape architect. He joined Andropoga and Associates in 1983 and has been a principal since 1995. Trained as a landscape architect and an architect, Jose excels at thinking outside the box while still unearthing the realities of innovative construction techniques. He's directed a wide variety of design and planning projects, from restoring urban parks to designing corporate campuses to planning new mixed-use communities. Regardless of the project scale, Jose distills the site's essential resources into designs that are functional, beautiful, and environmentally responsible. He's a visiting lecturer at Drexel University and at the University of Pennsylvania School of Design. He'll be speaking on recent projects as well as the development of standards for sustainable landscape design. Jason Smith is a senior associate principal at Kieran Timberlake Architects in Philadelphia. He's been with the firm since 1996 and has over 12 years of experience. He's a registered architect and a LEED accredited professional. He's currently associate in charge for the new physics building at Rice University, a multifamily development for living homes, and Jason heads up the comprehensive research initiatives for Kieran Timberlake. If you're familiar with their work, their research programs fit very importantly into their professional work. Jason will be speaking on regenerative practices in building design. And Ellen Watts is also a LEED accredited professional, as is Jose. I didn't mention that. Ellen is the co-founder of Architera, a professional architecture, planning, and real estate advisory firm dedicated to sustainable design and real estate and smart growth. A LEED accredited architect and frequent speaker on green buildings, Ellen and her partners Dan Ahrens and Daniel Bernstein had one of the fastest growing design practices in the Boston area. In addition to designing buildings, Architera conducts funded research on sustainable design trends and green building performance. Ellen will be speaking on innovative technologies for living buildings. So please join me in welcoming Jose Alminana.
Thank you, John. Well, thanks, everybody. I was pleased to see that there was a little pamphlet attached to the website of the conference with a series of concepts and some homework for you to do, and I hope you did, because some of the things that are listed there are concepts that I want to talk a little bit about it. Unfortunately, we don't have as much time as the subject deserves, nor do you have the patience for it, so we'll try to make this as pleasantly as possible. It's never hurt to be aware of where we reside and the things that have happened in the last 5 minutes of the world, and for which we have caused a significant amount of transformation. These are unfortunately unphotoshopped images from NASA. And for many years, I didn't have the guts to actually look at a more recent image, and I haven't seen a more recent image Although I did earlier this spring look at this one here. And I'm sure hoping that this is a well-photoshopped image by Google. But it's pretty scary, isn't it? To quote a professor of mine, Dan Jensen, MacArthur Prize winner of conservation biology, mankind won, nature lost. We've managed to actually leave our footprint in the entire globe. And at the same time, it's a very exciting time for all of us because making us aware of the possibilities and the responsibilities that lie upon our profession is quite significant and a great time to be alive. We seem to have forgotten that the concept of a way does not exist. Everything is here. Everything is around us. We completely depend on water. We are affecting water and the distribution in the planet of vertiginous pace. We just don't know what's going to happen with the events 3 days ago in terms of the water balance around the Earth, but 17,000 planes had to be grounded because of volcanic eruption underneath the glacier. What does it mean? We have no idea, but change is upon us, and we better embrace it and be ready, adaptive, and be quick to react and adapt ourselves to it, so the survival of the fittest is something that we can actually talk about it in the future. So for us, the issue of water, when we think about carbon footprint, energy footprint, and simply life, is at the core of our practice. And for those, I involve all designers that have something to do with the physical change of the lithosphere, which is this thin crust of the Earth where we all live on. There's only 1% of water available on the planet for us to consume and to sustain the human race. And our question is, what are we going to do with it? At the same time, we have a significant disconnect between what that lithosphere supports, which is fundamentally most of the life in the planet, and what we do with our built environment. It's a very simple cartoon here of what we tend to see in trees, having to sustain their lives outside of this building or in our urban centers. Well, on the left side, we have this incredible engine of energy and recycling and production of nutrients to support life. There's millions of living parts in a teaspoon of soil, and we think of soil as dirt. We think of soil as the one thing that we can manage and move at will without disregard for what happens there, and then we treat it as a commodity. Here it is. We're selling topsoil that we've taken away from a farm, a non-renewable resource, 150 years to generate topsoil, which is what fundamentally sustains most of life in the planet in one way or another. When we come to the building realm, in the built environment, we know buildings can do extremely well. We've heard all day today how buildings could be much better, and we know how buildings can have made strides in the last 5-10 years in reducing, for example, energy use. We still have a lot more to go: carbon emissions, water use, solid waste. But buildings at the end of the day will be perhaps with zero or neutral impact. They cannot contribute to a positive change because buildings are not alive. The only way to really be truly regenerative is to incorporate living systems in our buildings, in our sites, in our landscapes. There is an effort across the country to try to incorporate this idea of capturing the value of what happens outside of the buildings and making it in such a way that becomes an incentive for cities and for developers and for architects and for the people that are capable of changing the face of the earth to be able to do better. For example, this happens to be the Seattle Green Factor, in which the city of Seattle actually provides incentives to developers depending on the amount of green that is actually incorporated into the buildings, saving trees, providing green roofs, creating a trellis that supports vines, street trees, and so forth and so on. It's the first movement towards trying to really develop a series of strategies that actually can contribute in some form to the definition of value for the landscapes and the sites. You can't see this very well, but this hasn't gone unnoticed. And back in October last year, October 5th last year, President Obama issued an executive order where he's asking every single entity in the government to actually pay attention to all these things. This is an executive order that talks about federal leadership in environmental, energy, and economic performance. And if you read this, you will find out that many of the things that we're trying to do with buildings and with sustainable design and so forth are now part of what the government is actually asking themselves to do, and setting standards that are, in many cases, much higher than the current practices in our industry. So there are many ways to grade this. We know LEED is at the center of perhaps changing the marketplace in the most significant way, with a series of levels of attainment, silver, gold, platinum, living buildings, and ultimately restorative design. And I would like to add another circle to this called regenerative design, because in the restorative design, and we can argue about this, and it will be a nice conversation for later on, we're just restoring to what we have there before. When we're talking about regenerative, we're actually creating a positive change, which is long time overdue because of all the degeneration that we as a species have created in the planet. Here comes sort of a white knight, if you wish, which is an effort to actually begin to capture what sites and landscapes can actually be doing in terms of becoming more sustainable and regenerative. The Sustainable Sites Initiative is an effort that I was honored to be participate over the last 5 years in creating a rating system for site and landscapes that actually seeks out to rate the design, construction, and maintenance practices for landscapes of all types. Because every project has a site, but not every project has a building. So it will be interesting that we begin to think about sites and landscapes as a consistent, of every project, and not necessarily everything through the building lens. It is a very serious effort that is spearheaded by the American Society of Landscape Architects, the Lady Bird Johnson Wildflower Center of the University of Texas in Austin, and the United States Botanic Garden. Part of that steering committee includes the U.S. Green Building Council, the Environmental Protection Agency, yes, the American Society of Civil Engineers, Environment and Water Resources Institute. They have a seat on the table, and they have been participating in this for the last 5 years. There is a series of guiding principles that have led to the development of these guidelines and performance benchmarks. And of these principles, we've heard many of them. At the very top of it, the do no harm principle, or the use the precautionary principle. I'd like to call your attention to this one here, the provision of regenerative systems as intergenerational equity. That's a mouthful, but I think it's pretty easy to understand. It's what we're going to do now, so the ones that come behind us can stay a little bit longer on this planet, to put it in very simple terms. It does represent a paradigm shift in the way we look at resources and the way we go about, in this case, 4 large building blocks of resources that we have. The idea is that we move from a mindset of conservation to a mindset of regeneration. So, for example, when we look at water, we want to conserve water, reuse water, balance water, but regenerate water, create it cleaner, have water that is available for living systems to take advantage of. In energy, we reduce, we renew, we offset, but ultimately we want to produce. And habitat, we want to preserve, protect, restore, but we need to regenerate. And that regeneration may not be necessarily the way it used to be, because we are changing the way things are now on the planet. And with materials, we can't just reuse, and recycle. We need to upcycle and think about finding a better use or a higher use to the materials in the way we find them. So what it means is that we want to concentrate our efforts in this little wedge here piece. If we were to continue business as usual, we know that the amount of resource depletion in use is going to increase forever. And we know that there's a finite amount of this. But if we were to actually look at all these reduced environmental impact strategies, we can bring that trend down. And that's where we want to focus our efforts on. In terms of landscapes, when we think about a post-oil economy and we move into a carbon economy, this is a graphic here that describes the amount of carbon sequestration that is associated with different types of landscapes, from peatlands to wetlands, all the way down to freshwater deserts and urban conditions. And you can see that in peatlands is where most of the amount of carbon is actually stored in any kind of landscape, contrary to the perception that perhaps it's the tropical forest, the one that has the most amount of carbon stored. Well, it's not stored because most of the carbon is actually above the ground. But you can see here what happens in some of the wetlands and sort of what happens in some of the temperate grasslands. So landscapes all of a sudden become this commodity that can actually sequester carbon. And in doing so, provide nutrients, provide recycling, provide all kinds of things that may find a place in the marketplace. So when we look at a landscape, I think that we can begin to look at a landscape in a slightly different way. So we can do our customary analysis of looking through GIS mapping systems to things like elevation, slopes, and types of soils, vegetation, the intangibles about perceptions of the space and the views and so forth. But the landscapes actually begin to offer an opportunity to be managed in a different way. And the way they are managed, they are going to be requiring more or less input of resources, and at the same time reduce the carbon footprint. This is a fundamental issue for institutions that have decided to commit to carbon neutrality, which is the case of Middlebury College, where the landscape becomes another vehicle to achieve those goals. So we can map out what happens in terms of how many gallons of fuels are used for managing each type of landscape, how many labor hours, what is the quality, what is the capital expense, and what is the operations and maintenance over the years. So we have an economic impact in all of this. So we can think of landscapes from being bucolic and beautiful like this to being more diverse and rich and supporting a much wider plant community and diversity, and actually providing different places for expansion, for recreation. So the Sustainable Sites Initiative recognizes that landscapes are in a position to actually capture and regenerate ecosystem services. Ecosystem services being those that nature provides for all forms of life in the planet to be sustained, that occur from mountain and polar environments all the way down to islands in the middle of the ocean. So ecosystem services can occur in any one site across the globe. And what are those ecosystem services? Well, we know about it if you read that little pamphlet that was in the website. We have all these things that happen in landscapes that we are in a position to really capture, understand, and deploy systems that can actually replicate those. So you will ask, well, what are the attributes of a sustainable site? If we're going to talk about a sustainable site, well, it will be one that minimizes the resources transported to it and minimizes the materials that are leaving that site. In other words, it recycles as much as possible. That supports viable habitats, that promotes healthy ecosystems beyond the site's boundary because it's not actually acting by itself. It's in part of a significant web. That replicates natural processes of that reference size in case that site has been degraded. But we know what the site offers in other places that are undisturbed, and we can try to begin to replicate that. That enhances the quality of life of its users. There's a human component here. And it could perhaps act as a carbon sink and regulates other greenhouse gases. So the Sustainable Sites Initiative launched a rating system for sites and landscapes back in November 2009, where there is, similar to LEED, a rating system with 250 points. There's 4 levels of attainment. and there are multiple point levels for each one of the credits. The credits are organized in the way you conceive a project and you execute a project. From the early phases of a project where you have site selection and pre-design assessment, through credits that deal with the design component of the project, including site design for human health and well-being, not only material, soil, vegetation, and water. Credits that are connected to the construction process of the site. And then, last but not least, operations and maintenance and monitoring and innovation. There are a total of 16 prerequisites and 51 different credits, and they're all weighted in different scales. But you can see that the soil and vegetation, which is that interface between plant, soils, and water, it actually is the one that has the largest number of credits. And we went back and forth a great deal. This is actually the product of 5 years' worth of work that is now in the pilot project phase of its age. There are a number of prerequisites that are required. You simply have to meet these prerequisites in order to become a rated sustainable site. But some of them that I think are pretty important is that the bottom line for example, irrigation requirements, and this is a way to capture the industry and transform the marketplace. This may not be necessarily the end-all be-all, but it's a way to penetrate in the market and make it tangible. So this is actually the entry level, the prerequisite for the water management is what LEED is right now at the lowest level of the points system. But there are things like the creation of a soil management plan as we go through construction, and the plan for sustainable landscape maintenance, which is a covenant between actually the design team and the owner and the operations group that has to be in place in order for this to move forward. Because if we're going to design systems that are going to have to perform in a certain way, we need to make sure that we can actually put in place the maintenance procedures to follow up the changes and the evolution of this living system so the goals that we have in terms of performance are achieved. So you do a chart like you do with LEED, and you say, I can achieve this credit, not achieve this credit, this is not applicable, and so forth, and at the end of the day, you end up with a number of points. So I will just briefly talk about a couple of the prerequisites and a couple of the credits, and then we'll talk about 3 projects, one built, one under construction, and one under design. So as I mentioned before, one of the prerequisites is the Plan for Sustainable Site Maintenance, and if you go to sustainablesites.org, you will download a 300-page report that has all this information and tell you what you need to do and the forms and so forth. But an interesting credit here in terms of the human health and well-being that speaks to social equity is this one that actually requires or rewards projects that actually look at the way the wage distribution occurs under the contract of the building. So we want to encourage actually that the majority of the jobs that each project actually generates remain in the local community and remain in the local community at the lower levels so we can actually affect the largest number of people. In this case, economic equity and social equity come together. At the same time, we want to make sure that there's accessibility to this through a project that provides amenities that are accessible to the communities, that there are support for sustainable practice in plant production, there's support for sustainable practice in materials manufacturing, and that there are credits that actually have monitoring credits for monitoring the performance of sustainable design practices. So going into an urban environment, this is a project in Philadelphia, as urban as it gets. It's about 1.8 acres. It's a new facility for Thomas Jefferson University, a new building, and the opportunity to create a very large open space, largest amount of open space added to the city of Philadelphia since the creation of Independence Mall. What you see here is the size of a football field. What this project does is it takes the building and uses the building as a catchment, takes all the runoff from the roof of the building, the cleanest water on the site, takes it down along with the AC condensate to a cistern that actually provides irrigation to support all the living systems on top of this plaza. That uses soils that are 100% man-made, manufactured as the best management practice for stormwater management, where we can actually model the amount of water that is retained by those soils and actually avoid that water, that rainwater, to go into the combined sewer system and create problems with raw sewage discharge into the Delaware River. And here's some photographs of the project under construction with the excavation happening, and everything from this line to the west or to the left side is actually on top of a parking garage. It's designed in such a way that could be used at night with a tent that provides shelter for university activities, and it's used frequently by the community. Going to a brownfield, also in Philadelphia, where the idea is to actually create a project that has zero waste. This is an 11-acre site, a new community center for the Salvation Army. And the idea was to actually inventory everything that was existing on the site and try to find a way to upcycle those resources. So we looked at the supply and the demand, what is available, what do we need to use, and in which way the existing materials can actually become part of the new fabric of the site to support the new activities. We went through a series of strategies determining the type of recycling schedule and the standards that need to be met for the different types of operation. Look at cut and fill calculations that you can do very crudely with the yellow trays and colors, or you can be very sophisticated with computer models. Adjusting the profile of the site so we can actually end up with this, which is a supporting infrastructure that recycles most of those materials, that then supports a landscape, a high-performance landscape that manages water and provides amenities for the site. So this is a photograph from yesterday morning of the site, and you can see the various different types of soils being actually deployed on the site, providing access for circulation and stormwater management features, which then resulted in the change of specifications in the way we wrote the contract, the way we demanded, certain submittals and testing done from the project. And the results is that we use 100% of those materials that we recycle on the site. We ended up with a very low cost per square foot, $19 square foot for site development here. And we don't know exactly the savings, but we know that we save at least $300,000 in hauling and tipping fees for taking this out. So we look at the project in terms of the building as a catchment. It's almost 2 acres of roof surface, conveying that runoff through a series of cisterns that can direct that rainwater for irrigation, exhibiting that water in a series of surface runnels, so people are aware of what is happening when it rains, or is aware of what happens with the air condensates inside of the building, water condensates inside of the building. And then that informs the entire landscape with a series of rain gardens. And then the parking areas that are necessary to support this facility are paved with pervious asphalt as to minimize the amount of runoff that is generated by the building. So 99% of the storms are retained on site for the 2-year or less. This occurs in upwards of 92% of the time. For the 100-year storm, we reduce the flows coming out of the building, out of the site by 79%. And lastly, a project that is an interesting challenge is a brownfield renovation in Pittsburgh for the Phipps Conservatory. It is a project that is has challenged itself to meet the Living Building Challenge. I don't know if you are aware of what this is, but it is the next level beyond LEED that is now out there for people to meet. There are 18 prerequisites. You either meet them all or you don't meet the challenge. There's no way to get points here and point there. You have to meet all the prerequisites. And what we find interesting of this Living Building Challenge is that they are out of the 16 prerequisites, there are 13 prerequisites that are directly related to sites and landscapes. If you look at the LEED rating system, you can if you obtain all the water and site credits, you can actually get a building certified. and it's sort of hidden in the background there. But in this case, this project is built on this landfill, which has been used for storage in the facility. We went through extensive charrettes with users, community members, and the institution, as well as many members of the design community in the city of Pittsburgh. Ended up with a building project that has to be net zero energy, using a combination of different energy sources, many renewable strategies with solar, photovoltaic, ground couple heating systems, where the building is being designed to maximize daylight and actually natural ventilation as to reduce the amount of energy consumption, where every surface of the site is actually playing a role in contributing to the net zero water diagram, from capturing water for reuse to actually processing that water and actually cleaning the water that gets soiled by the use inside of the building, with a series of constructed wetlands. It is a site that is completely restored from scratch, because it doesn't exist there right now, with a series of walkways to accommodate a significant change in grade from the upper plateau to the lower plateau, about 3 stories high. At the bottom of it there is a water feature that actually is modeled after a lagoon, natural lagoon swimming pool, which you see here, where all the filtration of the water is actually done by living systems that are actually hosted by plants and roots and stone media, and then there's a filtration mechanism that takes the water through all this planted reeds and wetlands and actually cleans the water. This is a system that has been utilized in Europe for many, many years, and it's becoming more common here in the United States. Then there is a narrative for the landscape, where the landscape actually is restored to the appropriate types of plant communities, depending on where they are located on the site and the performance that they require to use. But in order to support these different kinds of landscapes, we need to create a soil management plan, which one of the credits that we need to comply with for sustainable sites. This project I failed to mention is a pilot project for the Sustainable Sites Initiative. And to do that, there's a series of areas that are delineated on the site and very tightly crafted specifications for performance of those soils that are deployed in those areas that are going to be planted in different ways to support a whole different variety of plant communities. This one happens to be in the one at the water's edge, along the rain gardens, the different plant material for the constructed wetlands that are going to clean the wastewater, the woodland gardens, and what happens at the ground plane, alkaline meadows, which are areas that are very hot and get very dry, that are going to tend to be with high pH. In landscapes, we don't talk about HP landscapes or high performance landscapes. We talk about pH, whether the pH is high or low, but we're all going to the same place. And then there is this inspiration education prerequisite that the project has to have, where we created spaces outside for enjoyment and for outdoor classrooms and so forth. One last important aspect of it is that we talked about the sense of place. And the sense of place is about how, over the years, this site has actually developed. And if you look at the way this cliff has developed, there's something very important about the way the rocks are actually stratified on the site. And to do that, we have a series of retaining walls that are actually mimicking the way the materials come out of the site, from less decomposed rocks and blocky shapes and forms at the bottom of the site to more stratified systems as the weathering occurs. So this is only about this cliff in Pittsburgh and nowhere else on Earth. These are some vignettes of the proposed landscape and an overall bird's-eye view with the 3-story building, the connection to the existing conservatory, a series of walkways coming down, and the lagoon at the bottom. This is the location for the constructed wetland, and then these layers of trees will be irrigated with the wastewater. And then in closing, I just want to leave you with this thought. It's a quote by somebody that you will all recognize in a minute. This happens to be limestone cliffs in Tasmania. So every single one of these living creatures here is hanging there for their lives. And it says, a thing is right when it tends to preserve the integrity, stability, and beauty of the biotic community. Isn't that what we all are about here? But it's wrong when it tends to do otherwise. This was written by Aldo Leopold back in 1949. That happens to be the way many people live in the city where I grew up for half of my life, in Caracas, Venezuela. And we don't want to end up there. We want to make life much better for these people as well. Thank you very much. Next, right? No, Jason Smith.
Thanks, Jose. Thanks, Jack. Thanks, everyone. Really pleased to be here near the end of the day because many of the things that I'll talk about in the next 30 minutes have been touched on by people who are far more expert than I. And so one of my distinguishing characteristics today is that most people here that are talking are much smarter than me. And what I'm going to try to do is touch on simple strategies. And if I had a title for this lecture, it would probably be Simple Strategies. Things that we do in our practice and things that other practices and other communities can embrace in order to allow ourselves to work more broadly, more holistically, and as the title of the symposium suggests, in a more integrative way. So the initial concept of how we conduct that work is a network, a sort of neural network diagram that suggests that none of our actions can be taken independently of others. And so we talk about things that are related to place and resources. We talk about things that are related to energy and economy. We talk about things that are related to design, process, and human ecology. And unfortunately, I can't talk about all those things today. But I'm going to try to cut across a broad swath of these things so that we can all talk about the ones that are most important and most prescient to this audience. So unlike most of the times I talk, I'm not going to talk much about design. And I'm not going to talk much about economy. The others I'll try to talk about in the context of how we conduct this search. And you see in the upper left, I'm not sure what the little splash BG there is, but we seek to do all of these things in a closed loop system. And so we design, we innovate, and we invent through the processes of planning our work, doing our work, monitoring our work, and then closing the loop by learning from our work. And we think that, I think as Jack suggested earlier, that the capacities of designers to learn and continue to learn are something that we continue to propagate and are interested in. So the initial question is, what do we mean by beyond lead? I was really pleased to hear Malcolm talk about the evolution of lead that's forthcoming. And lead has developed, for better or worse, into an approach much like a Chinese menu. Right? I'll take a little bit of this, and I'll take a little bit of that, and I'll take a little bit of that, and I'll put it all in a brown bag, and I'll bring it home, and it'll be called a meal. And so whether you're picking from the Happy Family menu or whether you're picking from innovative wastewater technologies, I think all of us in this room can agree that beyond this, there's a broader and more holistic goal. Now, the way that we approach that goal in our practice is that we take lead as a starting point, and we speak about it as a good initiation for rules of approximation. And for years, for decades, for hundreds of years, the quantification of data in our profession, whether it's architecture, engineering, landscape architecture, civil design, or structural engineering, all had to do with these rules of thumb. We all learned them in school. We all learned how a beam acts as a structural engineer, or we learned similar facts in any one of those other professions. LEED takes and capitalizes on those rules of thumb in a way that makes them more palatable and more digestible. And that's a thing that has brought, as Malcolm suggested, LEED and environmental design into the human consciousness on a much broader scale. But frankly, we believe in moving beyond LEED through deep simulation. And so simulation of the way our buildings work and operate is something that, again, Steve and Dave and others can talk about on the energy side in a much more informed and intellectual way than I can. But we believe in propagating that through the early phases of design. And so we try to understand the predictive elements of our behavior as designers and as building users through a series of simulations and number crunching, if you will. And the solution set that leads us to when we talk about the process of what we mean by beyond LEED is standard practice is this little egg, hopefully diminishing every day. You know, hopefully the rules of standard practice are no longer adequate. And so we look for solutions through algebraic approximation. These are things that LEED is really good at capitalizing on. So many credits for this percentage in reduction and so many credits for this percentage in improvement. That algebraic approximation is, again, a good starting point and something that we can all relate to. But we believe that solutions through simulation is a way to move beyond that in the capacity of proving out before we build the building, before we construct the landscape, before we connect the pipe. And what that gives us is a really large solution set, one that's quantifiably larger than the solution set we started with any of those other three things independently. So what are some of the strategies? And this will be a recurring theme in the talk. What are some of the strategies that we look for moving beyond LEED? Well, first of all, we use a multiplicity of them, right? And none of us can work in a vacuum. None of us do work in a vacuum. And so that multiplicity of strategies spreads across all of our constituent users, consultants, building users, building owners, and folks that use our buildings every day. Considering your carbon output is something I'll touch on only briefly. Again, it's a measuring stick that we're all seeking to absorb in a way, sorry, pardon the pun, but we are certainly focused on it. Analyzing your ecological footprint so that the sorts of things that Lori and others are doing here at Dartmouth that helps make that data more palatable and more understandable and more recognizable to folks in their everyday lives. Life cycle assessment is something that we relied on for a long time, but there are now different methods of life cycle assessment. So traditionally, life cycle assessment had to do with payback periods, quantifiable, measurable financial payback periods. But now life cycle assessment has to do with the sort of things that other speakers have talked about. How do we reserve these quantities of limited resources that we have? What's the life cycle payback of that? And site and program resourcing, which I'll talk a lot about, which really has to do with understanding the site at an explicit level and the program at an explicit level, and not letting those two things be divorced from one another, but letting those two things inform one another. So can we build a carbon neutral building? We think about this as a series of wedges, right? And any search towards carbon neutrality or zero energy or any other topics we're talking about today can't be done by one thing. I mean, frankly speaking, a building itself can't be carbon neutral, right? We couldn't construct a building of any sort unless we gathered sticks and stones and piled them on top of one another without any sort of glue or adhesive or mortar that was completely carbon neutral. So one of the things that we talk about is what can we do through design? But these other wedges, place, resources, energy, human ecology, process, and economy, all bring us incrementally closer towards a more perfect and carbon neutral building landscape site. Now, one way we might look at that, this is a data collection piece from a project we're working on just recently for the State Department. And one of the things that we look at is, okay, standard design, and what are the incremental steps away from standard design for this particular building, in this particular context, for this particular user group that can get us towards there. So the EPC is a system that's used extensively in Europe to quantify the carbon output of buildings and developments. And so by taking a little chunk, a little wedge from each of these things, whether it's lighting, or whether it's the filters, or whether it's adding a combined heat and power solution, whether it's photovoltaics. Each of these things incrementally works towards the broader whole. And as you can see, one of the really wonderful things is at the end, you have an equivalency of use. Remember some of the slides from Steve's presentation, you saw some really measurable things. I mean, oil took up such a large point of it. What we're trying to do is bring those things into parity so that they all can be identified as equivalent constituents. Now, how do you do that? Well, one of the ways is through design. The other ways is through external factors. So, giant energy hogging, carbon spewing car, like the Porsche Carrera, essentially emits the same amount of carbon dioxide as we can sink in almost 2-hectare swath of old growth forest. Is that something that's really sustainable for us? Is it sustainable for us to drive those kind of cars? Is it really sustainable for us to offset those sorts of things, sink those sorts of things? At the same time, we look at a structure from a project we did in Philadelphia and the production of the steel structure, which in our area of the country, like most areas of the country, is done by coal-fired plants. How do we offset that with an off-site usage? How do we look at what it takes at? And so 20 hours of energy production in a wind farm is actually something that's going to be far more attainable in our current environment than starting to dedicate old growth forests to sink carbon. So we start to look at these as a multiplicity of strategies. Now, how do we do that in the built environment? Well, let's just say, like others have today, that we're going to design a building that's going to last for 40 years. Well, the building in and of itself, let's see where this is. The building in and of itself has this much embodied energy in it. Right? We can improve on it. We can use lower embodied energy materials. We can use lower site process materials that use less energy. We can transport less. But we're still going to get to a point where we're never going to be able to build a building that doesn't have X amount of embodied energy in it. The rest of this stuff, with various benchmarking attached to it, is all about how well your building performs after you sink all that embodied energy into it. Right? So is it a zero net energy building? Does it give back to the grid? Is it just an average building? Does it hit the 2030 target building? All these various ways that we can quantify how it is that our operational energy builds upon our embodied energy. But importantly, and this is something that most of the building community doesn't reflect on, is how do we recover that embodied energy at the end of a building's life cycle? So it's something that in our practice we've been really focused on, and it's a practice that routinely builds for folks like Dartmouth who want buildings that last forever. We still ask the question about how do we recover that energy? Because we'll never get to what we call energy neutrality if we don't understand how it is that we recycle, repurpose, reuse buildings and their constituent parts at the end of their lifespan. So operational energy is really only half the problem. Through this, we establish our footprint metrics. We plant trees, right? I mean, we can't make peat bogs, so we plant trees. We look outside the immediate environment for offsets, right? Wider, more globally. We do simple things, and remember, simple strategies, encouraging alternative means of transportation. We choose our materials carefully. And then most importantly, and this works so well at a place like this institution, we educate. Because we try to make sure that everyone learns through the process and that we learn from the folks that we're working with on a day-to-day basis. Now, the last in the sort of general simple strategies, how do we build without generating waste streams? So we wrote a book about this that reflected on other industries that are far less primitive than the building design and construction industries. Industries that for economic circumstances or for circumstances of their very survival have found new and better, improved ways to build. And almost universally, those industries have built in one way. They haven't built with pieces and parts. They've built with larger scale modules. Some of the industries call them chunks. Some of them call them modules. But it's an approach that in the last decade we've sought to understand as it pertains to buildings. What it means is that on the top diagram, you see a conventional building construction, where all these different things come to the site. They come in all sorts of trucks, they come in all sorts of dollies, people unload them and offload them, and then all this waste goes out of the site. It's a completely uncontrolled environment, even in the best of circumstances. So we seek to adopt the methodology that the airplane industry uses, the shipbuilding industry uses, and other vertically integrated industries use. And that's to bring the materials to a centralized location and to control the waste and control the streams that move off of that location in a way that is much more elegant. Now, if we build buildings and we design landscapes, we're never going to be able to do that inside a factory vacuum. But what parts of the building, what parts of the landscape can we contain in a way that's highly controllable and minimizes our waste? And I included this slide to make everyone aware that this isn't just tin buildings that we see outside. I mean, we've had the privilege of working with some institutions that want to push this far enough, and I should recommend this to Dartmouth, that actually brittle masonry buildings can be built this way. It's a structural steel frame that's imported in large chunks, and the building pieces are knit together at one of the other Ivy League institutions. The other way we do that is how do we do it locally, right? So as practitioners of the art and science of architecture and design, we're used to going through a catalog and saying, I want this, 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 and this, and we don't really know where it comes from. Yeah? Well, how do we integrate that, and how do we work with our clients? And Jose and I have enjoyed a long and collaborative relationship on projects at Middlebury and elsewhere. And for folks like Middlebury and Dartmouth who are looking out more broadly at their own land holdings, we understand that we can be using those things inside the building. And then finally, again, how do we look at the building itself being recycled? So how, in the end, do we understand that the building itself can be recycled, and we can grab back the embodied energy that's gone into the building and not just minimize the operational energy? Okay? So many of these strategies are going to be familiar to folks. Developing a recycling plan, considering off-site fabrication, because it dramatically, 80+% reduces the amount of waste that comes out of a construction site. Reusing materials from the site, as Jose mentioned on, designing for recycled materials, and then understanding those life cycle impacts. Important question that we ask all of our clients: what do we mean by here? Okay. This is a diagram that maps the thermal comfort conditions in Hanover, New Hampshire. So this is the thermal comfort band, and this is where you spend most of your time. It's obvious to most folks here that in a heating-dominated climate, you're going to have a different energy demand. You're going to have a different programmatic demand than you might have in another climate. So the first thing is, where is the climatological data, and what can it tell us about what we can do? So for a project we worked on actually in an earlier edition of the Thayer Dining Hall, we started off with Jack and others' assistants looking more widely at the precinct, looking at the precinct that was part of the larger swath of New Hampshire and even Vermont that the college occupies, and then developing that into a precinct plan so that we could identify not only the typical architecture and urban plan issues that you see highlighted here, but also relationships in and among the entire campus network. So how do we define here by that? And then when we started programming the building, we quickly came to an understanding that we could hybridize the program together with the environmental data, together with the sense of place. And so in a pure stacking diagrammatic way, we knew that we had a building, to use Dave Madigan's terminology, that'd be a big energy hog, right? Thayer, even the most improved Thayer Dining Hall is still going to use a tremendous amount of energy to do what it has to do. But we looked quickly and rigorously at how we might develop a stacking diagram to suggest that the orientation of the building and the constituent program of the building and the climatological data that we knew about here in Hanover quickly suggested that before we came to a building design, we knew programmatically what we had to do in order to organize the building. As an example, we knew that during the summer, we would need to seek, because the early part of the building, the building would face in the early part of the day the intense eastern sun. While in the winter, we wanted to try to capture that heat. So the design of a thermal transfer wall that would be a modern improvement on the classic trum wall that would gather the heat in the winter and release it to the building, that would gather the heat in the summer and release it to the atmosphere, was the initial starting point. The programmatic stacking diagram that allowed us to take heat-generating spaces, i.e. the kitchen, and stack them below heat-receiving spaces, at least for most of the part of the year, if you remember that diagram, also allowed us to develop that symbiotic relationship where one part of the building that's generating a tremendous amount of heat is feeding another part of the building that wants to receive a tremendous amount of heat. And so we try to do that as part of the early and pre-design effort. So in understanding what we mean by here, we seek to be anthropologists of all sort, to understand the culture and the ecology of a place, to understand the social and academic fabrics as well of that same place. We try to move out from beyond our typical training as architects and designers and get into just enough science to really get us in trouble. And so geomorphology and climatic and microclimatic analysis are important things to try to gather in those initial data sets for us. Mapping the local DNA and listening are, again, important parts of the process that historically we haven't done well as a firm. How do we extend that out to the entirety of the design team? So this is a typical work plan, conventional work plan for a design and construction project. You can see the crescendo of everybody's labor happening very late in the process, right? So the architect is starting off with some bubble of work, and that goes in fits and starts. The consultants are usually fed after the architect has a so-called schematic design. The contractors come in late to the stuff. Everybody is trying to work at the very last minute to try to get a building designed and constructed. We propose a paradigm that's much more in equilibrium, in which architects, clients, consultants, contractors, and all other user groups are fundamentally drawn together at the beginning of a process, in that pre-design phase, to work in a participatory manner so that the hump in the curve is not back here, but here. And then the net benefits of that accrue to the rest of the project. So front-loading work in the front part of the process is integral to the approach. So how does that work in the same Thayer project? Well, we knew that we had an opportunity to use this preheat zone in a passive way in the building, but we also knew that the building would be filled with active systems, right? Like sciences buildings, the reason that these buildings are so energy consumptive is because you have air that's constantly moving through them to evacuate the kitchen and hood equipment, especially in a large dining hall. So we worked with Dave and others to try to understand how we might use those same strategies that I talked about, but in a way that also was more broadly distributed through the building system. So we were tremendously excited about this building to be able to accomplish a dining hall with operable windows, right? Sounds simple, but it's not something that's done conventionally, right? Because of the air requirements and because of the temperature control requirements. So in this stacking diagram, if you'll recall, we had the notion that we could feed underheated spaces with overheated spaces. Well, we also had the notion that we could feed underventilated spaces with overventilated spaces. And so you can see, for example, that that middle area, which contains the kitchen, is actually drawing air from other parts of the building and passively and actively moving air across it. We also, much to the chagrin of some at Dartmouth, built a vertical building and tried to take advantage of the natural effect, both the stack effect and the natural ventilation effect, in order to bring this building into a full ecological circle that includes human ecology. So we exchange information with our consultants in that way early in the process and often in the process. We seek to develop long-term relationships with our clients and with our consultants. And I think all of us on the design side here understand the value of that, not only economically, but also from a project teaming respect. And speaking of respect, we bring everyone to the table early and value everyone's opinion equally. And then on the other side, we share the attribution of these systems. Importantly, as others have said, we work to design a process for each project that's done prior to the design of the building. So the process isn't a static thing that travels from one building project to another. It's something that varies from project to project. Okay, what components of the building can we do away with altogether? It's a question we should ask ourselves altogether, all the time. Similar to psychometric data from in this case Hanover, but again, you can see most of the time in the heating zone, and most of the passive strategies and active strategies that are low energy can capture most of the temperature comfort data points. But what happens when we extend that out more broadly? This is a project at Middlebury College, and for those of you that know it, this is on the north end of the college, and it was a project that we worked on with Jose and others to design a new residential commons. So the very first act of siting this building, which the master plan suggested we plug right in here, was an act of understanding the building systems approach. These are buildings that, under normative conditions, because of Middlebury's really active and really world-acclaimed summer language program, have air conditioning as a de facto circumstance. Right? They're bringing people from all over the world, including people from much colder areas and much hotter areas, and they're putting them together in an environment which is essentially sealed from the outside in a Middlebury summer. And so we started to ask questions about how can we improve on that, and can we do away with this fait accompli that was air conditioning, and how do we do it in a way that is exhaustive in terms of its research, but also appropriate in terms of the user group. And so simply speaking, we started with an argument about spatial economy, right? All of the room that air conditioning on these buildings take was costing X amount of dollars, was costing X number of energy to run, and we just developed a simple diagram that was a sectional diagram that didn't have anything to do with the plan of the building, but realized that flow-through natural or mechanically assisted natural ventilation would be spatially much more or much less consumptive than any sort of diagram that include chillers and air handlers and the ventilation requirements. We then designed the plan of the building to reflect a flow-through ventilation system so that these ensuite arrangements can be opened in a cross-ventilated way. So speaking of that integrated design, the MEP system doesn't always have to start with the things that you know. It can oftentimes start with the things that you don't know. The more practical things about reducing solar gain and using thermal mass and creating a building footprint shaped and oriented for natural ventilation are things that we've forgotten as a design profession. Simple strategies about the way to orient buildings and the systems that we use in buildings are things that we are bringing back to the fore. How do we measure that performance? Well, here's a simple diagram that the folks from SLC will probably be familiar about. Standard practice, which we're trying to get away from, best practice, advanced practice, and then cutting edge practice, or you might say regenerative practice. And in order to measure that, we use tools that are not sophisticated to many of the user groups here, but tend to be fairly straightforward from an architect's perspective. The slide's not coming out well, but this was another piece of the Middlebury project in which we were trying to identify the backup wall system. And the folks at Middlebury were concerned about issues of condensation as they related to a structural steel and an infill stud metal frame. And so we designed an elegant analysis and a supremely inelegant analysis. So the elegant analysis was done by architectural testing in York, Pennsylvania, and it modified the dew point, condensation factor, and temperature profile of the anchors, which happen to be those ferro anchors that Jason mentioned earlier from Canada. And then in our own very primitive way, we sought to seek how we can improve upon that by actually insulating the anchors themselves. So looking outside the box from a tool set that suggests there's one set of data, but then from a model set that suggests there's a second set of data. Similarly, for a project I'm working on in a very different climate in Houston, Texas, we look at the building facades both integrally and individually, and we set goals for each facade. In the same way that Jason talked about the window-to-wall ratio, we're looking at other issues about how to construct each facade and the entirety of the building envelope in a way that's comprehensive but tuned to the local microclimate. So we use all sorts of different tools, some sophisticated, some primitive. We measure on multiple scales. We use science, or as close to science as we know, which is to say we put out a hypothesis and then we try to go about experimenting and proving that hypothesis before the building is built. Others will come along after the building is built and be able to prove whether we were good about energy intensity or whether we were bad about energy intensity. But testing that hypothesis before you actually get to it is really in the true sense of experimentation. And then how do we balance energy demands for large, very, very energy-intensive buildings? And like your life sciences building here, we know that building systems are no longer a small portion of what they were when most of these campuses were built, or actually the majority of the building systems and the building components. So we look at basic strategies that we all know and love, VAV systems, VFD systems, and clustering space by conditioning requirements, and we take that as a given. So we cluster the building in order to put the opaque, highly sensitive, highly temperature-controlled labs in one part of the site, and the daylit, much less highly sensitive, much less temperature-controlled offices in another part of the building. And then we look at more broad-based cutting-edge systems, like desiccant systems, and as Dave suggested, other systems that come from other more advanced building societies. And then we try to stuff them all into the building, right? And this is one of the most difficult parts. How do we predict accurately how much space we're going to need for all this stuff? So this comes from our Revit model of the project in Houston. And most of the engineers and contractors on the job site are wildly proud to proclaim is 1/6 of the largest air handling unit ever to go into a building in the state of Texas. And that's shown right here in red. The important part, the germane part to our discussion is that pretreatment unit, the unit that does 80% of the bulk dehumidification in this very humid, very hot, very solar-intensive climate, actually reduces beyond what we could do with a more distributed strategy with several smaller air handling units by about 30%. So the inversion of what we think, bigger equipment, more expensive equipment, more energy-intensive equipment, in this particular case, has proven out and is proving out to be more efficient. So how can our architecture generate energy? Okay, right now the current methodology, we have infrastructure, it feeds buildings, right? This is a campus much like Dartmouth. We look at a green building, which is built a little better, and the infrastructure bubble grows slightly. Well, down here we look at another version of that in a new building, which is more conventional. The infrastructure grows less slightly and more comparable to these. And then we look at what we might call a generative building, a building that might generate electricity or other resources and feed back in. And so similarly for the project in Houston, we looked at opportunities for wind power. We looked at opportunities for solar power. And remember, we did this with a multiplicity of tools that suggest that we're using common software that are available to test, for example, whether we wanted to reject the solar load from this particular building or whether we wanted to adopt it and use it within the building. So strategies that might be applicable there, utilizing CHP, utilizing wind turbines, integrating the building form with renewable energy systems, i.e. turning the part of the building that wants to receive solar gain in the right location and the part that wants to reject it in another location, and then deploying integrated renewable energy sources, not just ones that are tacked onto the building, but ones that are integrated. I'll finish up briefly by talking about process. How do we imagine this building as an experiment? Right? So how do we do the things on the front end that hypothesize and prove out that science, and then how do we monitor the building afterwards? And this is an area where the research arm in our practice is really investing heavily. And how do we monitor buildings after they're existing? Not the conventional building automation system things that most people here are familiar with, but other issues. So for example, that 2-bar building at Rice, how do we take the building and know where we use daylight, but then monitor the incident daylight in a way that helps us to reform the systems, and in this case, helps us to understand in a predictive model how we might generate a self-shading facade. And then as a corollary, how do we take that energy, and if, like the institutional decision was here, we're not going to invest in photovoltaics because of the price of electricity generated on their campus, the low price of electricity, how do we then creatively reject the heat from areas that don't want it? Looking at a multiplicity of strategies for doing that, taking the incident solar radiation, and then testing that out through a series of mock-ups early in the design process that determines whether or not this is going to prove out. This happens to be a terracotta system, which our most simple analogy is that acts like a radiator. Right? It absorbs solar energy, then it reflects back solar energy before it enters the building. It's a nested rain screen assembly that has double redundancy in terms of its water shedding technology. And importantly, we build it, and we build it early. So this is an early mock-up that we did in our office. And this is the on-site mock-up. This mock-up is forming not only the basis of design for the project, but also undergoing a series of solar studies with sensors placed in it so that we can be accurate about the predictive behavior of this particular facade. So we look both forward and back. Right? And we develop those criteria early on for what is acceptable on a cutting-edge fashion and what really is bleeding edge. We try to innovate, we invent we really don't look in magazines. We collaborate. We combine art and science in the best way that we know how. We combine intuition and analysis in the best way how. And this is one that we like to talk about because it's important to us. When we're going to fail, and we will fail, we all fail at these building projects, but we want to fail early. So we set up those predictive models, whether they're electronic and virtual or whether they're pragmatic and real, to fail early in the process and fail quickly in the process so that we have the opportunity to recover and initiate and integrate the systems that are appropriate for the building. Thank you.
We do have time for a few questions, so we'd like to try to wrap up at about 5:45.
This is a question for Jose. Regarding the Sustainable Sites Initiative, how do you see that, or do you see that integrated with the LEED rating systems when you roll it out? And particularly for landscaping with regard to buildings.
I'm sorry, can you repeat that? I didn't hear it.
With regard to the Sustainable Sites Initiative, do you see that, or how do you see that integrated with the LEED rating system? Particularly for landscaping associated with building construction?
The U.S. Green Building Council has been a participant in this effort from day one, pretty much. The plan is to integrate this system in the V3 version of LEED. Currently, the report was reviewed by the Technical Advisory Group of the Sustainable Sites, and that received their endorsement. So all these strategies and all these benchmarks and guidelines are going to somehow guide, the next round of requirements for sites and landscapes and water on LEED.
Could you tell us more about the Living Buildings Challenge for those of us who are not architects? That sounded really interesting.
Well, it's hard to describe very quickly, but it is about a building or a project. A Living Building Challenge first started by using building as a verb, as a building that lives and that does things, to sustain itself. It is a building that actually generates all the energy that it produces, that it uses, that captures all the water that it generates, that cleans all the water that it actually needs to use, that restores the habitat that it displaces, that it serves as a sort of inspiration and beauty, that has a strict compliance with the list of materials that are not able to be utilized in the building, what they call the red list. And I will encourage all of you to look at the Cascadia Green Building chapter. Is in Seattle, I believe, is their headquarters. It's the Northwest Green Building Council chapter that was the group that actually issued this challenge. There is one building that actually has been built that has met this criteria, although the full certification of this building will not be given until after 1 year of operation and after ascertaining that all the goals have been met. But it's actually a very difficult and very challenging level of compliance, particularly when it comes down to the management of the water that the building is polluting itself, because the environmental regulations are not up to speed to allow for this to happen. So we have to build more of this project to demonstrate that this is actually feasible, so the regulatory climate changes and we can actually go on the business of reducing water consumption and energy in that regard.
Yes, hi. I asked a question earlier in this session about unifying urban landscapes with the goals of zero net energy buildings. And it seems to me that the technologies available today don't really allow for an urban level of density. And I think it's really important to try to unify urban density with smart building design, because places like New York City are the most energy efficient and least polluting places in the world. I mean, New York City is the greenest city in this country. When people think of New York City, they think of a horrible urban sort of mess. And it's important to note that getting out of your car and having a livable, walkable community is the way forward. And I'd like to see this idea of this concept unified with that idea. So, and if you guys have any input in how you guys can move forward to do that, I would be interested in hearing
I would
that.
like to offer just one comment. We often do projects that are similarly challenged to the ones you're talking about. There's simply just not enough site area or solar access or workability to be delivering wood pellets into inner city locations. I think we're going to need lots and lots of decentralized and centralized solutions. We're going to need everything we've got to lick this climate challenge. And a project I didn't talk about, but I really hope everyone in this room is generally aware of, is the new wind technology testing center on Boston Harbor. It's a project that we're designing. It's about 6 months from completion. Just finished a continuous 3-day concrete pour for its mega foundations. It's a first of a kind in the world. And it's going to bring the possibility of offshore wind to the northeast, which has premier wind resources. And this holds the hopefulness, I think, that we're soon going to have the possibility of affordable renewable energy power. There are many, many interesting hydro developments, land wind developments. I think that we can look forward to a lot of promising technological advancement on the centralized system side. If we have low-load buildings, the renewable generation doesn't need to be on site. Thank you.
I think the parking garage down by Jefferson Medical Center is really a wonderful, innovative educational tool. But I'm wondering, isn't a sustainable parking garage kind of an oxymoron?
Yeah, it could be seen that way. I often wonder what it could be if we wouldn't have to drive a car, right? There were, I think there were close to 400 parking spaces actually provided on that side, with a 3% pervious area on that entire block. And that was counting on all the trip hits that actually were built on top of the parking garage. So a pretty, as unfunctional of a landscape as you can ever dream to have one. This building actually builds, this project actually accommodates a much bigger building that didn't used to be there. There's only 240 parking spaces, so there's a reduction of that. And it offers, you know, an open space that the campus, and for that matter, that part of the city doesn't have. I think that, you know, to go to where we need to get to, we're going to have to change our modus operandi in many fashions. You know, as long as we have no investment in public transportation, as long as we don't think about densifying and repopulating cities that have actually lost population. Philadelphia can accept 1.5 million people without having to build one single square inch of road or add any more pipes, and it's right there in the middle of megalopolis. It's This is the kind of attitude that I think we need to have. I mean, I think that the solution to the future in this planet is going to be in our urban centers, you know, densifying our urban centers. But a lot of things are going to have to happen to move us away from the car. You know, it's not good enough to have a Prius, you know, and use less energy. You know, this is not the way we're going to be able to get around this issue. But we'll do one at a time. The important thing is that we do projects that we can see, we can fail at doing, and we can get better when we get to do the next one. I was just mentioning to Jason that, you know, some of the projects that you see built here are projects that were designed 3 or 4 years ago. And if we were to design those projects today, there's 3 or 4 years of learning, and we would do things very different. You know, so we're in a catch-up game, you know, from the minute we open our eyes, unfortunately.
I'm afraid we're going to have to draw to a close at this point. Please join me in welcoming, in thanking these panelists as well as all of our speakers today.